Let's continue with the examples for rotational axis of symmetry. We have considered water molecule, how the rotational axis has to be passed from the center of gravity, and how do we rotate. Usually the rotation should be in clockwise manner. Anti-clockwise or the counterclockwise manner can also be done, but for convention we always go by clockwise direction. We will take up more examples so that the concept will be much more clearer for you. So, we start with some other example. Let us start with ammonia. Well, whenever we draw ammonia, for our convenience we can take one of the structures. So, usually when we put ammonia, this is how we can draw ammonia. This is one way to draw. There is also another way which will be more convenient for us to show the rotational axis, or even we can show planes very easily. Well, suppose if I take this particular diagram, I am not representing the lone pair. So, both represent ammonia, but they are in a different view. In this view, if at all we want to rotate, that will not be much convenient to show it on a paper or a board, but this particular schematic representation, it will be much more easier for us to show the rotational axis. So, we will be going with this particular structure. What kind of rotational axis, or what is the order that is present in ammonia, we will check. In the beginning, these molecules may look very simple, but again we have to work out all the structures. So, once we put it in our mind, then the remaining things become easy. So, let me put H1, H2 and H3. How are we holding it? Now, you can just look at the molecular model. This is the first way that I am holding. This you can imagine it as a lone pair of an electron, and these are the 3 hydrogens, the central atom being the nitrogen. This is one way to hold. The another way to hold is, I am just holding it this way, where the 3 hydrogens are facing towards you, or I can also hold it another way, where the 3 hydrogens are facing away from you. In either way we get the similar structure. So, in this case what I have represented is that the 3 hydrogens, they are facing towards you. Now, as I hold the molecule in this manner, then you have to search for the rotational axis. So, it is now, this is the top view. Suppose if I am holding the ammonia in this manner, this is a top view, and you can imagine z axis along this direction. This will be z, x and y direction. All the atoms do not fall on every axis. Suppose if I am taking z along this axis, a lone pair and the nitrogen are falling on it, and suppose if this is the x, only one of the hydrogen atoms is falling, whereas the 2 other hydrogen atoms do not fall on y or x, because it makes a 120-degree angle, whereas the angle between the coordinates is 90-degree. Okay. Next, now once I am holding it this way, the same rotational axis which was here, I was passing it through the nitrogen and the lone pair. Now, as I hold the molecule in this way, the same rotational axis, now it is facing towards you, right? Now, it is facing towards you. So, as it is coming through the nitrogen, so how should I represent this rotational axis? Means, since it is pointing towards you, what you can only see is like a point, you just cannot see it like a line. So, for this reason, if I want to show the rotational axis in ammonia where the 3 hydrogens are facing towards you, and if this is the rotational axis which is pointing towards you, simply have to put a point, and around this point we are doing the operation called as rotation. This is how we have to represent if the rotational axis is pointing towards you. Next thing, the 3 hydrogens, they are equidistant, they have a triangular relation. So in the stereographs, what I have discussed is, when there is a linear relation between the identical atoms, probably there will be a C2, and here are 3 identical atoms equidistant and they have a triangular relation. So logically going, you can have a C3 because there will be a 120, 120 and a 120 degree angle of separation. So once there is a 120 degree angle of separation, then I have to rotate 3 times so that I get an identical configuration. For the first 120 degree rotation, I get an equivalent configuration. Second 120 degree rotation, I get another equivalent configuration. And when I rotate for the third time to 120 degree angle, then I will end up with an identical configuration. It means I have to perform 3 different operations so that I get identical configuration. So let us perform all these 3 different operations. I am taking theta as 120 degree because there is a triangular relation. Now once theta is 120 degree, from the Cn which we discussed in the last class, 360 degree by theta, or you can say 360 degree upon theta, theta is 120. So this becomes 3, n is 3. Hence we can say there is a C3 rotational axis or 3-fold rotational axis in ammonia. So I have represented theta equal to 120 degree, it is a C3. We are rotating in a clockwise manner. So as I am rotating in a clockwise manner, you can just watch, H1 will take up the position of H2, whereas H2 will take up the position of H3, and 3 will come into the position of 1. So all the 3 hydrogens, they are shifting from their positions, but the position of the nitrogen is intact. Nitrogen is not shifting its position because the rotational axis is passing through nitrogen. What we discussed in the coordinates, whenever the rotational axis passes through the coordinates, that coordinate do not shift. So in a similar way, whenever the rotational axis is passing through some atom, that atom will not shift with, or that atom will not exchange with any other atom, but in itself it is rotating. Nitrogen in itself is rotating, but it will not exchange with any other atom. Okay. Then let us look at the structures. 3 hydrogens are still facing towards you. Lone pair is not being represented. It is understood that there is a lone pair. So 1 has come to the position of 2 since it is a clockwise rotation and even numbering is in a clockwise manner. So once you represent 1, then the next number should be 2 and 3. This is another easier way to remember. So whatever structure that we got, it is not the same as the first one. So we say this is an equivalent structure. Why it is an equivalent structure? Supposing that I remove the numbering 1, 2 and 3. These are 3 hydrogens, these are also 3 hydrogens. Both structures look the same, but they are not the same since the position of the hydrogens is changed. So we say it is an equivalent structure, and operation has to be done until we get an identical configuration. So I am further rotating it. Let me rotate by another 120 degree. This is a 3-fold rotational axis which I am operating for the second time. Right. Now we still have a structure which is not identical to the original one. So let me perform one more rotational operation and let's check whether we get an identical configuration or not. So let the theta be 120 degree and it is another third fold or a three-fold rotational axis. You can see that H1 will come into the position of H2. So whatever structure that we got here, if you can just compare it with the original one, it is just looking the same. 1 is at the position of 1, 2 at 2 and 3 at 3. So you need not do further operations. You can just stop the rotation operation here because you got an identical configuration which is just the same as that of the original one. So here you can stop. Now whatever structures that we got, we can just number them. Starting from here, suppose if I number it as 1, 2, 3 and 4. So the first and fourth structure, 1 and 4, this pair they are identical. You choose any other pair, such a pair would be equivalent. Suppose if I choose 1 and 2, these two are equivalent, 1 and 3 are equivalent, 2 and 3 are equivalent, 2 and 4 are equivalent, 3 and 4 are equivalent, but only one pair will be identical in every molecule, that is the first one and the last one. So any other pair other than 1 and 4, it will be an equivalent pair. Let me give a couple of examples for this. You can also write any other equivalent pair here. So this is how we have seen the rotational axis which is present in ammonia. I am just showing it again with the model. Right. I am trying to hold the model in this manner. Hydrogen 1 facing above, 2 and 3 towards your left hand side and right hand side, and all the 3 hydrogens are towards you. They are coming towards you. This is the rotational axis that we are passing, and I rotate by 120 degree. All these rotational axes are imaginary. Whatever symmetry elements that we have chosen in the beginning, as I said, all these symmetry elements are imaginary elements. So you can just imagine that there is a rotational axis here, and around this rotational axis we are doing the or performing the rotation. First 120 degree, right? You can concentrate on one of the hydrogens. You just take the reference of one of the hydrogens. So let me start it from here. You can take this direction or this direction. Suppose if I am rotating it this way, this is clockwise to me, this looks anti-clockwise towards you. Okay? So in your view, let me show it this way. Take this reference. I am rotating by 120 degree. I got an equivalent structure. Rotate by another 120 degree. I got second equivalent structure. Rotate by third 120 degree. I got an identical structure where the hydrogen has come to its position. So we have rotated it 3 times and we got an identical structure. This is for ammonia. Once we have completed this rotational axis, then you have to check for any other rotational axis present in ammonia. We have seen there is a C3 rotational axis which is valid. You can also check whether there is any C2 or not. So suppose if I am holding ammonia in this way, I am trying to pass a C2 rotational axis passing from the nitrogen and one of the hydrogens. I am now not holding it this way, I am holding it this way. Okay. So when I hold it this way, this rotational axis, you just pass it through the hydrogens, one of the hydrogens and the nitrogen. Then we try to rotate it by 180 degree. We'll try to check whether C2 is present or not. So when I try to rotate by 180 degree, on paper it may look like C2 is present for some students, because wrongly if we represent ammonia in this way, here the 3 bonds are looking like in plane, but ammonia is not a planar molecule, it is a pyramidal molecule. Since it is a pyramidal molecule, we cannot put all the 3 bonds like a solid structures. I mean, you cannot just put a planar structure for ammonia, it is a wrong geometry. For this reason, in the beginning we said one of the prerequisites is geometry of the structure, geometry of the molecule that we are choosing is to be known. So without geometry you cannot go for the symmetry elements. Suppose if at all you take this kind of a wrong structure, then you may visualize C2s present in it. C2s will be present if at all you choose such a wrong structure, but in this case you can check. I am holding it this way. When the rotational axis is passing through nitrogen and hydrogen, now these are the 2 hydrogens which are not in plane, but they are towards you. There is a lone pair which is away from you. As I rotate by 180 degree, now what you see is lone pair is now coming towards you, whereas the 2 hydrogens which were towards you, now they are facing towards me. So whatever structure we got, this is not an equivalent structure to the original one. So for this reason we say there is no C2 which is possible in ammonia. Had it been planar, then you would have got some C2s. But ammonia is non-planar, it is pyramidal structure, therefore no C2 is present. Also there is no other rotational axis, whether you check for C4, C5, there is no other rotational axis. And you need not check for C1, because whichever molecule that you choose, you rotate it by 360 degree, you will definitely get the identical configuration when you rotate by 360 degree. So every time we need not say that all these molecules will have C1, we simply put there is an identity element, because identity is a doing nothing operation or a doing complete operation. So with respect to rotation, it is a 360 degree rotation. 360 degree rotation, 360 upon 360 will be 1. That will be a C1. So C1 is just equivalent to identity. So wherever we have identity written, it is just equivalent to C1. C1 is innately present, you need not go for it. This is with respect to ammonia. So we have seen 2 simple examples, one is H2O, the another one is NH3. And in both these cases we find one rotational axis. Let me take up a planar molecule. Now let us start with BCl3. All the 3 chlorines are in the plane of the board. So it becomes a planar molecule. Planar, it is non-linear molecule. Now in this case, it is just different to ammonia, where in ammonia the 3 hydrogens were either facing towards you or away from you. It is a pyramidal structure, but BCl3 is a planar structure. So once I say planar structure, then if you can visualize, if you can imagine, you may find more than one rotational axis in it. What are those different rotational axes? We will see, but prior to that we will first check this rotational axis which is pointing towards you. I am trying to pass it through boron. There is a triangular relation between the 3 chlorines. All the 3 chlorines are identical and they are equidistant. Once they are identical, equidistant, triangular relation, then you can imagine C3 to be present in it. Then we have to check. It is just like trial and error. So I am imagining that there is a C3. let me put a C3. I try to rotate. If at all I get a equivalent structure, then we say C3 is present in it. So this C3, theta is 120 degree, it is a C3. Similar to ammonia, 1 will be shifting into the position of 2, 2 into 3 and 3 into 1. So this is the structure that you get, and structure 2 and 1, they are looking similar. Only the position of the chlorine is changing, but it is looking similar, therefore this becomes an equivalent structure. Hence C3 is present in it, so we can further go on operating this C3. Once we enter into point groups, you need not work out each and every example and then you have to check whether it is equivalent or identical. Just by looking at the molecule whether Cn is present or not. If at all Cn is present, what is N? That you have to say within seconds. Every time you should not put all the structures, it will eat away our time. We got another equivalent structure. Now here we got a structure which just looks same as that of the first one. Position of 1 and 1, if you want you can just highlight it. In this position there is 1, at that same position we have 3, we have 2, now we got 1. So whatever reference position that I have chosen, the reference position which I have highlighted in yellow, in that reference position there was a chlorine 1. Again when I get 1 in my reference position, then we can assure that we got an identical structure. So that you can see in the second or even third, in second and third we have 3 and 2, whereas in the last structure you can see presence of 1. So this ensures that we got an identical structure. There you can stop your operation. After that you can just compare which particular pair is equivalent and which one is identical. As we said, there is only one identical pair, the first and the last. Remaining any other pair will become equivalent one. So with this we can confirm that there is a C3 present in BCl3. Let me show you the model. Right, here is a molecular model for BCl3. The central atom is considered to be boron and these are the 3 chlorines that are present. So instead of holding the molecule in this way, it is convenient for us to draw in this manner, because if at all I hold it this way, now this will be the top view. So showing the rotational axis become difficult, whereas if I draw it in this manner, then showing the rotational axis will become very easy. So this is your rotational axis. Since this is the rotational axis, it has to be like a point around which the rotation operation must be carried out. So we can just take one of the reference chlorine atoms, and with that reference chlorine atoms we try to rotate. So I am holding that reference chlorine atom. This is a 120 degree, second 120 degree, and a third 120 degree. So we got a structure which is identical to the original one, right? So this is how we can say there is a C3 rotational axis present in BCl3. Now there is a comparison between ammonia and BCl3. In ammonia we have C3, even in BCl3 we have a C3. But there is also a difference. Ammonia, as we said, it is a pyramidal structure, but BCl3 is a planar structure. Now since it is a planar structure and also there is no lone pair to one of these sides, Only if the lone pair is present, that has become pyrimidal in ammonia. Here there is no such lone pair. So what I try to do is, this becomes a C3. After that I try to pass a rotational axis from one of the chlorines and the central atom boron. Then if at all it is a C2, we try to rotate it by 180 degree, and once I rotate it by 180 degree, we have to check whether we are getting an equivalent structure or not. Now when I pass it from here, you can check it. This is a chlorine and a boron. That rotational axis is passing through chlorine and boron. So that chlorine and boron will not exchange their positions. Within itself they rotate, but they will not exchange with any other atom. So we just forget about the chlorine and the boron. Come to these two chlorines. These two chlorines are identical, and these two chlorines have a linear relation. So once I am passing a rotational axis, there are two other identical atoms which are equidistant in the sense only two atoms are there. So definitely they have a linear relation. With this linear relationship, I can visualize a C2. 90 degrees absent, but 180 degrees present. So as I rotate it by 180, I am getting an equivalent structure. I rotate by another 180, I get identical structure. So we can say that there is also a C2 along with a C3 rotational axis. I am just showing it again. Suppose if I am holding this chlorine as a reference, which is towards your right hand side, I rotate it by 180 degree, now it is moving towards your left hand side, it is an equivalent structure. I rotate by another 180 degree, now I am getting it towards your right hand side. This is just identical to the original one. Here I stop the operation. We say there is a C2 which is present. A question arises, how many rotational axes are present in BCl3? Now slowly we are arriving at the answers. We have seen a C3 which is passing only from the boron. We have also seen another rotational axis which is a C2 which is passing from one of the chlorines and the boron atom. But if you can look at BCl3, it looks very symmetric, and we can see the three chlorines are equidistant with a triangular relation. So if I am able to pass a C2 rotational axis from one of the chlorines and a boron, certainly there can be a C2 that can be passed from a second chlorine and a boron, third chlorine and a boron. It means there is a C3 from a boron. Also there is C2 from one of the chlorines, second chlorine, third chlorine. So it means there are 3 C2s and 1 C3. That is our conclusion. If we choose BCl3, this is a representation, schematic representation for a BCl3 C3 rotational axis, threefold rotational axis. For that same BCl3, let us choose a C2 rotational axis passing from boron and one of the chlorines. Right, what we find is this is passing through boron and chlorine, they remain there itself. This chlorine 1 will not shift with any other chlorine. So chlorine remain intact. 2 and 3, now as I rotate, 2 and 3 will exchange. So this is the structure that we get. Whatever structure that we got is an equivalent structure. So you should not stop here. Let us pass another rotational axis and rotate it by a 180 degree angle. When theta is 180 degree, that become a C2. Two and 3 get exchanged upon 180 degree rotation, so they come to the same position. structures 1 and the third one, they look identical. Here you can stop the rotation operation. That is your final structure. So our conclusion is, along with C3 we also have a C2, and that C2 is passing from one of the chlorines. Since all the three chlorines are identical, if there is a C2 which is possible from one of the chlorines, the other two chlorines along with boron should also have C2s. So based on that assumption, we altogether have 1, 2 and 3 C2s along with a C3. Okay. So I am trying to represent all the 3 C2s in one structure. This is one, the other two will be from here and from here. So the overall structure I am representing. Let me also represent a C3. That C3 is passing only from the boron. This is a C2. Likewise, we also have another C2 passing from a second chlorine. Similar way, we also have it from Cl3. So there are 3 C2s. To differentiate them, we can just label them as a C2, C2 prime and C2 double prime, or simply we can say there are 3 C2s along with a C3. One C3 plus 3 C2s. In BCl3 we have one C3 along with 3 C2s. Now in some books you can also see another representation of this. What we said is, this chlorine 2 is being exchanging with chlorine 3. It means if this is the chlorine, one half of the chlorine or whichever chlorine is towards you, as I rotate, it is moving away from you. It is just moving away from you. So the back side of the chlorine you can see now here. Suppose if this is the 2, right, as it rotates, now it is coming here, this is the other side. So for this purpose, I said if at all you take a reference, plus means that half which is towards you in the first structure will move away from you. Let us just put minus, that is only our reference point, it is not a charge. So as it moves again, now it is coming towards you. So to represent this, in some books what we find is, suppose if this is the boron, I am trying to rotate the boron, 180-degree rotation is also going through this boron. So let me put boron this way, because the boron is also rotating. This chlorine is rotating. Now this is a chlorine 1. This chlorine has come to this end, so just let me put that chlorine 3. And this is a chlorine moving to that end. This is a chlorine 2. So this is just a representation so that the beginner can understand, though boron and chlorine 1 are not exchanging with any other atom, but in themselves there is a change, there is a rotation. If this is this boron, in itself it is moving, so that is represented here. Chlorine 1 is not shifting with any other atom, but in itself there is a rotation. So again that is represented here. 3 is coming, but the other end is coming, therefore 3 will be represented just as its mirror image. Even Cl2 is going as its mirror image. But if at all we draw this kind of a structure, it will confuse you as well as even the examiner. So this is only for our understanding purpose, to understand that all the atoms are shifting their phases. Even this boron and chlorine, which is not shifting with any other atom, in itself there is a shift. If that understanding is with us, then it becomes very easy. You need not put any such structures. This will be only for your understanding. Here also let me introduce one more point. What we have done is we have taken a 180-degree rotation for the first time. We have also done another 180-degree rotation for the second time. These we are calling it as C2s. But for our convenience, what we will do is, this is C2 for the first time. I have rotated it for the first time, so I am putting it as a C21. This is for the second time, so just let me put it as a C22 for our convenience, because this has a little importance which comes later. For the first time, if you rotate, you just put 1. For the second time, if at all we are rotating, you may put it as 2. So this has two important consequences. One is, when I say C21, it is a 180-degree rotation. When I say C22, it is actually a 360-degree rotation. Because when I directly put C22, that simply means this we are not considering. Directly from here, if I make a C22, we get this identical structure. So if I say C22, it is a 360-degree rotation. If I say C21, it is a 180-degree rotation. But here we are just differentiating this for the first time we are operating, therefore I have put C21. This is for the second time we are operating, therefore I have put C22. That is the only difference. If you can just go back, for BCl3, there is a C3 rotational axis. So how many times did we operate that C3? If you just go through C31, it was a 120-degree angle. We had a C32. We also had C3 for the third time. There we got an identical structure. So when it was a C3, we have operated for the first time, second time and third time to get an identical structure. If it is a C2, we are operating for 2 times and we are getting an identical structure. We will also check with some other molecules. Suppose if I have a C4 rotational axis, and if at all I am getting an identical structure after doing a C4-4 operation, then we will come to some conclusion. Right. Let us just compare ammonia and BCl3. In ammonia, we only had a C3, whereas in BCl3, we have a C3 plus 3 C2s. So there are 4 rotational axes in BCl3. There is only 1 rotational axis in ammonia. Now we will just conclude one more point here. This is a generalized example. Suppose if I am alone in this world, I don't need any name because no one has to call me. But suppose if there is a second or third person in this world, then definitely we need some names so that we can differentiate ourselves with the other persons. In a similar way, when there is only 1 rotational axis, you need not differentiate it or you need not identify it. It is simply as a rotational axis. But there is more than 1 rotational axis, then we have to show some difference between them. So to show such a difference, what we have taken as a convention is, whenever you have more than 1 rotational axis of different fold, this is a C3 3-fold, this is a C2 2-fold. Whenever we have more than 1 rotational axis of different fold, then we have a guideline. The one with a higher fold, should be called as a principal axis. Don't write it as principal, it is not PLE, it is principal axis. Whereas the one with a lower fold, it is considered to be secondary or auxiliary. Or you can call it as a subsidiary axis. So whenever we have more than one rotational axis with different fold, then the one with a higher fold is called as a principal axis, whereas the one with lower folds, they are called as a secondary or auxiliary or subsidiary axis. When it comes to ammonia, there is only one rotational axis. So for our convenience to name it, you can directly call it as a principal axis. There is only one axis and that axis is named as a principal axis, whereas in the case of BCl3 we have a principal axis as well as 3 subsidiary or secondary axes. So keeping this in view, let us take one more example. So for this purpose you have to remember this guideline. Let me take an example of ethylene. Well, ethylene is a non-linear but a planar molecule. Now, let me put it more symmetrical, right? It is a planar molecule, and as we visualize it, we can see that there is some rotational axis which can be passed between the two carbons. From here, if at all we can pass, because one CH2 unit is just looking symmetric to another CH2 unit, they are planar. Suppose if this is not in the plane, it has come outside, then we say the two units are non-symmetric. But the two CH2 units are in plane, then maybe I can pass a C2 from here which is pointing towards you. And if at all I rotate by a 180 degree, I may get an equivalent structure which we have to check after drawing. Also, if you look carefully, there could be another rotational axis other than the one which is pointing towards you. Since these two halves, they look symmetric, so if at all I pass a rotational axis in between the two carbons again, I rotate by 180, I get an equivalent structure. The first one is this which is pointing towards you. Now the second one is this which is between the two carbons but in the plane of the board. Along with this, I can also find, or I can also imagine another rotational axis which is passing through two carbons, and the upper half can exchange with the lower half. So these could be the three rotational axes present in ethylene molecule, right? So let us try to represent all the three rotational axes, and whether they are present or not we have to check by drawing the structures. Let us go with the first one. Now this is pointing towards you. Let me start from here, and if at all I rotate by a 180 degree, I have to get an equivalent structure. So let me put it as a C2. And this is a C2 for the first time I am operating, therefore I am just putting it as a C21. I am not directly writing which atoms are being exchanged, I will just take some time. So once I put the other structures, you can just pause the video, and what you have to do is you have to just try to check what structures will come, whether they are equivalent or not, you have to check. So let me give another structure. This unit looks very wonderful because it is mostly applicative, and much of the inorganic topics are theoretical, but this particular one you can see it as an applicative one. So this is the first rotational axis which is pointing towards you. Second one is in the plane of the board between the two carbons. For all these things, the angle of rotation is 180 degree. It is not being changed. So whether or not you are getting an equivalent structure, you may just work it out. Meanwhile, I am showing you the model. Right. Here is a molecular model for ethylene. For convenience, we may hold it this way in our imaginations. If at all you have a model, you can just hold it this way, or you may also hold it in this manner. You may also hold it in this manner, as you like. Once you are aware of the coordinates and from where the rotational axis has to be passed from, you may hold it any way as you like. But this is the most convenient way because we can draw it easily over the board. Once I am holding it in this manner, the two black ones are considered to be the carbons and the four white ones are considered to be the hydrogens. It is a planar molecule but a non-linear one. Now the first rotational axis that we are showing it is pointing towards you. It is between the two carbons through the bonds. It is through a pi bond. Now the rotation is this. This is how we are rotating. This is the rotation. Or if you can just imagine, here is the rotational axis. You may just check which opposite atoms are exchanging with one another in this rotation. Now if I am taking one reference, suppose if this is my reference, where is this hydrogen atom entering into? You just check. This is towards your bottom right. As I rotate this, now it is moving towards your top left. So bottom right into top left. Okay. Now coming to this second one, it is again between the two carbons but in the plane of the board. Now as I rotate, it is in the plane of the board molecule. I rotate by 180. It is giving you an equivalent structure. You just look at the atoms that are shifting. Suppose if I am taking this reference, right, this is your top right reference. Now where is this top right reference going? Previously it was going to the bottom left. Now in this particular rotation, it is going towards your top left. Did you get the point? From top right, it is going into top left. So this is another different rotational axis. Now the third one is passing through the two carbons. This is how we are just passing imaginary rotational axis. So if at all I am taking the top right with respect to you, I am choosing the top right hydrogen. As I rotate, it is getting into bottom right. So all the three rotational axes are different. This is what we can conclude. How are the atoms shifting? I have told you. So based on that, simply you have to put the position of these hydrogens. Okay. Second point. Now the first rotation was this. This is an in-plane rotation. We call this as a in-plane rotation. In-plane rotation in the sense, suppose if this is in the plane of the board and if this is your rotational axis, as I am rotating it, the molecule is within the plane only. So we call such rotations as in-plane rotation. When it comes to the second rotation, it is out of plane rotation. Suppose if this is the plane of the molecule, as it is rotating, it is moving out of the plane, again it is coming into the plane. So this is called as a out of plane rotation. All these things have to be remembered because this has some importance in group theory and character table construction. This is an in-plane rotation. Now this one is an out of plane rotation. So this is the rotational axis out of plane. This is the rotational axis in plane. Third one is through the two carbons. It is also an out of plane rotation. Suppose if this is the plane, now it is moving out of the plane, again entering into the plane. So in ethylene we have three different rotationals. One is in plane rotation. This is the in plane rotation, whereas the other two are out of plane rotations. Okay. So keeping this in view, let us write the positions of the atoms. 1, 2, 3 and 4. Now this is the rotation. What we have seen is these two will exchange. So 1 and 3 we will put, and then 2 and 4 in the first case. In the second case, these atoms will exchange. So 1 and 4 are exchanging, 2 and 3 are exchanging. In the last case, top and bottom will exchange. So 1 will exchange with 2 and 3 will exchange with 4. So what we have to do is, whatever structure that we got is only an equivalent structure. So let us perform this is the rotational axis, and in the first case this is the rotational axis. This is a C2 for the second time. So once I am rotating it for the second time, 1 and 2 are getting exchanged, we are getting the original configuration. Even in this case, 4 and 1 exchange, 2 and 3 exchange, you get the original configuration. Even in the first case, when I rotate, 1 and 3 will exchange, 2 and 4 will exchange. So what we finally get is we get an identical structure. So this is how we can conclude which kind of rotational axes are present in ethylene. The answer is it is a planar molecule, nonlinear one. It has 3 different rotational axes. Now let us compare this ethylene. Let's compare this ethylene with BCl3. In BCl3 we had a C3 and C2. How many C2s means we had 3. In the case of ethylene, we have only C2, 3 in number. There is only a C2 rotational axis, but the number is 3. So previously we said whenever there is only one rotational axis, you need not name it. But if at all there is more than one rotational axis, then we have a guideline saying that whichever rotational axis has a higher order, that is to be named as a principal axis, and whichever rotational axis has a lower order, you can just call it as a fold, and whichever is having a lower fold or a lesser one, it is considered to be as a secondary axis. In the case of ethylene, you have more than one rotational axis, but the fold or the order of all the rotational axis is 2. You can just see it is a 2-fold, there are 3. Instead of putting 3 C2s, just let me put it as C2, C2 and C2. So there is more than one rotational axis, and every rotational axis is a 2-fold rotational axis. Then I cannot apply the same guideline which I have applied for BCl3. Higher fold, principal axis, lower fold, secondary axis. In this case, all rotational axis has the same fold. Then we have a second guideline. For such molecules, we have a second guideline. What that second guideline says is, when you have more than one rotational axis of the same fold, then that axis which is passing from more number of atoms is considered as a principal axis. I am just repeating the point. The second guideline says, whenever any molecule has more than one rotational axis of the same fold, then in such molecules, that axis which is passing through more number of atoms is considered as principal axis. Just look at the first one. In this case, the rotational axis is not passing through any atom. It is just passing through a pi bond. Even in the second case, it is only passing through a bond, not through any atom. Whereas in the third case, the rotational axis is passing through 2 carbon atoms. So if at all we have to prioritize, then definitely this will get some priority because it is passing through 2 carbon atoms, and this can be considered as a principal axis. So in ethylene, we have one principal axis and 2 subsidiary axes. Okay, this is how we conclude. But ethylene has always been in a little bit of controversy, because whenever we go to character tables, this is not taken as a principal axis, but instead the other rotational axis is taken as a principal axis for different conventions. But as a beginner, what we have to learn is, we have two guidelines for molecules with lower symmetry, where BCl3, ethylene, water, ammonia, all these fall under lower symmetry molecules. Whenever we have more than one rotational axis of different order or the different fold, the one with a higher fold is considered as a principal axis, and the one with a lower fold is considered as a subsidiary axis. Suppose if the molecule has more than one rotational axis with same fold, then the one which is passing from more number of atoms is considered as the principal axis, the others are considered as subsidiary. So this is considered as a principal, the others you can consider it as subsidiary. So this I can call it as a C2, this could be a C2 prime, C2 double prime. That is how we can conclude. And again I am passing a C2 for the first time, second time I am getting identical structure. First and second, 2 times we are performing, we are getting an identical structure. This is about ethylene. So this is a molecular model for ethylene, I am just showing it again. You can have different views of this ethylene. All these models, as you see, you have to just imagine the model, and once you imagine, try to imagine the symmetry elements that are present in it. This is another view. So you should be in a position to pass symmetry elements in whatever view that you take up. Well, we have seen C2, C3. We will take another example for C4 rotational axis. One of the best examples that we can choose from inorganic chemistry is PtCl4, tetrachloroplatinate. And while putting the structures or drawing the structures, you need not represent any charge here, because this is only for symmetry purpose. If at all you want to represent, you may just put 2 minus, but it is not required for us. We are only trying to get the symmetry of this particular molecule. You need not go with the charge. Now before I put the structures, you can just take a while. You can check what different kind of rotational axes that are present in this. PtCl4. The logic that you have to remember is, from the stereographs, what you find is, platinum is the central atom. There are 4 other atoms which are bound to platinum, and all these 4 atoms are identical. They have a square relation. If you can look it very carefully, they have a square relation. So to look at the square relation, just let me put the same PtCl4 in a different view. This is another view. You can check the square relation between the identical atoms. So here visualizing square, if it is difficult, then you may draw another structure. All this is for our convenience. So the logic goes, it is a planar molecule. There are 4 atoms that are identical and that have a square relation. In such a case, C4 has a greater probability. C4 is possible since it has a square relation. So where is that C4 that you have to check? That C4 will be passing through platinum. This is how it will pass. In this case also, this is how it has to pass. Okay. Now here I show you the molecular model for PtCl4. Platinum as a central atom, chlorine 1, 2, 3 and 4. Either you may hold it this way, there is a square relation, or you may hold it this way. So with reference to you may just imagine it as a plus or like a into multiplication symbol. So there is a square relation of identical atoms, therefore C4 has a greater probability. Where is that C4? We have to check. I am not holding it this way. Suppose if I hold it this way, then there has to be a top view. From this top view, then you have to rotate. That top view could be difficult now, so you may hold it in this manner. There is a rotational axis passing from the center of platinum, because every symmetry element has to pass through the center of gravity. So every time we don't repeat center of gravity, we simply say center of the molecule. It is passing through the center of the molecule, which is the platinum center. Then I rotate by 90 degree. I am getting an equivalent structure. Suppose if I rotate by say 10 degree, 20 degree, 30 or some 45 degree, 50 degree, I am not getting any equivalent structure. If at all I rotate by 90 degree, then I am getting an equivalent structure. So I say that there is a rotational axis and I am rotating by 90 degree, therefore I am calling it as a C4. 360 degree upon 90 will become C4, four-fold rotational axis. Now if this is my reference, in this reference you can just check one rotation, second rotation, third rotation, we got equivalent structure. This is my reference and this is for the fourth time I am rotating, then I am getting an identical structure. So what we conclude is in PtCl4 there is a C4 rotational axis which is passing from the central atom called as platinum. It is perpendicular to the plane of the molecule. Suppose if this is the plane of the molecule, it is just perpendicular to the plane of the molecule. There is a C4. So you may just look it carefully. Along with C4, if you can visualize any other rotational axis, you just try to access your brain. How many rotational axes can you see? You just take some time. Meanwhile, I am taking this particular structure and I will write the C4 rotation. C4 theta is 90. C4 I am operating for the first time, so I am putting it as a C4 1. One is getting into the position of 2. Now whatever structure that you get, this has become an equivalent structure. So what I try to do is, let me pass C4 for the second time. Theta is 90 degree. This is a C4 for the second time. Whatever structure that we got, it is still an equivalent structure, because in the first structure that we have chosen, 1 is towards your top right. So with reference to you, again when I get 1 towards your top right, at that time I have to stop the operation. Now you can just check whether we have ended up with an identical structure or not. My reference position is 1, where I got 4 in the first structure, which is replaced by 3, which is replaced by 2, now which is finally replaced by itself 1. So there we can end up. Then I can say that I got an identical structure. So to get an identical structure, how many operations have we performed means, we have performed 4 different operations, C4 for the first time, second, third and for the fourth time. So this is taken as one of the best examples to show C4 rotational axis. Along with C4, what we also find is there are C2s which are present in this. There are also C2s. So where are those C2s, we will try to find. Now if I am holding the PtCl4 in this way, C4 was passing only through platinum. C2s, it is passing from Cl, platinum and a Cl, which are linear, they are in line. Now from here if I rotate by 180, you can just check, I am rotating by 180, then I am getting an equivalent structure. Rotating twice, I get an identical structure. So if this is my reference, which is towards your right hand side, if this is my reference, I rotate by 180 moving towards your left hand side, rotate by another 180, I am getting it towards your right hand side. So there is a C2 rotational axis passing from chlorine, platinum and chlorine. This is one C2. Now if these have a linear relation, 2 chlorines are identical, these 2 chlorines, they have to be identical because both are chlorines with a central atom platinum. Let us try to pass a C2 from here then. Rotate by 180, I am getting an equivalent structure. Then I confirm that I have a second C2. The first C2 was passing from this. The second C2, it is passing from these chlorines. So I confirm that there are 2 C2s. One from chlorine, platinum, chlorine, another from this chlorine, platinum and chlorine. If you can very carefully see, along with these 2 C2s, you can also find some other C2s. So to visualize, it is just like this. From here there is a C2, another C2 is here. So if I pass a C2 from here, how should I rotate? For beginners it may look little bit difficult. Then instead of holding it this way, you may just hold it this way, or you may imagine it in this manner. Once I put it in this way, now there is a C2 between the chlorines, between these 2 and these 2, there is a C2, right? I am just rotating by 180, equivalent structure. I rotate by another 180, I get identical structure. If this is one C2 which is passing between these 2 chlorines, there is another C2 from here. Rotate by 180, you are getting an equivalent structure. Rotate by another 180, we are getting identical structure. Okay. The same thing we will try to represent on board. I am showing just one of these representations. Suppose if this is that PtCl4, let me take it as 1, 2, 3 and 4. That C2 rotational axis is passing from Cl1 and Cl3. This is for the first time. So we are putting it as a C21. Since this rotational axis is passing through 1 and 3, 1 and 3 do not change their positions. But 2 and 4 do exchange, they are exchanging with one another. Whatever structure that you get, it is not an identical one, so we simply call it as an equivalent one. Then what we do is try to perform another C2. This is a C2 that I am performing for a second time. 1 and 3 they do not change their positions, but within itself there is a shift which I need not show every time. Within itself there is a shift, but 2 and 4 they are again exchanging, and the structure that you get is identical to the original one. Here you can stop the operation. This is passing from Cl1 and Cl3. There is also another rotational axis that is passing from Cl4 and Cl2, where 1 and 3 exchange. So every structure need not be represented. One if I am doing, the second one you must be able to do. This is the one passing from 1 and 3. There is a second C2 which is passing from 2 and 4, that you should be able to produce. This is one type. Now the second type, which I represent it here, for convenience I have changed the structure pattern. In this case it is looking like a plus, it is looking like a multiplication symbol, so that we can show the C2 easily. Now that C2 is passing only through the platinum. Then we rotate by 180 degree. It is a C2 for the first time. These two atoms exchange 1 and 4, 2 and 3. What we are getting is an equivalent structure. So we should not be satisfied with this. Getting further, rotate by another 180 degree. This is a C2 for the second time. Then we get a structure that looks identical to the original one. So here we can see there is a C2 which is passing only from the platinum in plane with the molecule. Here is a C4 which is perpendicular. This is perpendicular to the plane of the molecule. C2s are in plane with the molecule. There are two types of C2s. One C2 is passing from 3 atoms. There are 2 such C2s again. Another type of C2 is passing only from the platinum. There are 2 C2s again. This is one. This is a second one. Here this is one, this is a second one. So altogether we have 4 C2s, 2 types. If I call this as C2, C2, you may call this as a C2 prime and a C2 prime. Just a differentiation for our convenience, because this can get a greater priority. It is passing through 3 atoms, whereas in this case it is only passing through 1 atom. So if at all any priority has to be given within these two, this must get a priority since it is passing from more number of atoms. Though this is passing only from 1 atom, since it has a higher fold, this is always considered as a principal axis. Okay. So I will try to represent all these rotational axes in a single diagram. There is one C4, two C2s, Let me put it as a C2 prime. Altogether we have 5 different rotational axes. One is a C4, the other 4 are C2s put into 2 different groups. One is passing from 3 atoms and the other one is passing only from 1 atom. This is about a C4 rotational axis example. So for C2 we have seen water molecule. For C3 we have seen the basic examples ammonia and also BCl3. We have also worked out ethylene, so that we have compared 2 guidelines where BCl3 as well as ethylene have to be compared. What 2 different guidelines that we have given is, all these molecules, these are low symmetry molecules. So whenever such a molecule has more than one rotational axis of different fold, then the one with a higher fold is to be considered as a principal axis and the ones with the lower fold must be considered as a subsidiary axis. One of the best examples that we have given is for BCl3. Then we have seen an example of ethylene where we had more than one rotational axis but with the same fold. In such a case, the one which is passing from more number of atoms is to be considered as the principal axis, whereas the other rotational axes are to be considered as subsidiary. So in such a case, the one which was passing from 2 carbon atoms was considered as the principal one, whereas the other 2 which were passing between the 2 carbons are considered to be subsidiary. Later, coming to the higher fold, we have taken an example of PtCl4. Within this PtCl4 we have seen a C4 rotational axis passing only from the platinum. Then we have seen 4 different C2s where we are putting them into 2 different pairs. One pair is passing from 3 atoms, 2 chlorines and a platinum. The other C2 is passing only from the platinum. Along with this, we can also see some more examples in our later classes. Right. After C4 rotational axis, we will just take some more examples for a higher fold rotational axis. Now, as we proceed towards higher fold rotational axis, the number of examples, they drastically drop. Suppose if I take a C2, C3 or C4, we find more number of examples. But as we go for a higher fold C5, C6, 7 or 8, the number of molecules are very low, but we will try to discuss 1 or 2 molecules. To show a C5 rotational axis, one of the easiest examples that is chosen in most of the text is taken this way. I can show a pentagon, but if at all it has to be a molecule, usually cyclopentane for C5, cyclohexane for C6, that will be shown. If it is for C7, C8, cycloheptane, cyclooctane will be shown. But if at all we look at the stereochemistry in the sense, not about the chiral centers that I am speaking, cyclopentane cannot be a planar molecule due to the presence of Bayer strain. It cannot be in plane. So once it is not in plane, it becomes difficult to show the rotational axis and C5 will not be present since it is not in plane. But just for symmetry considerations, cyclopentane is generally taken as a planar structure. So instead of cyclopentane, what we can do is, instead of choosing a cyclopentane one, let us choose a CP, cyclopentadienyl anion. Since it is aromatic and therefore it has to be a planar structure, and the structure also look very symmetric. In this we can visualize a C5, and that C5 is pointing towards you. There is a 72-degree angle. Here is a C5. There will be a 72-degree angle, and all the operations I am not performing. Simply I am putting 1, 2, 3, 4 and 5. Though there are hydrogens, but since it is a skeletal structure, all those hydrogens are not being represented. only I am giving the positions for them 1, 2, 3, 4 and 5. Theta is 72 degree and it is a C5. This is for the first time. When I perform C5 for the first time, what structure do we get is this one, where the position of the atoms is shifting. So one is taking up the position of 2 and every atom is shifting in itself. It is getting exchanged with the other consecutive atom, right. Whatever structure that we got is an equivalent structure, so further operations have to be performed. This is a C5. So this is C5 for the second time. I am taking the reference as this 1 is on top, and until I get 1 there, we have to just go on writing the structures. So that 1 is replaced by 5, 4, then we get 3. In the corresponding structures we will get 2 and finally we will get it as a 1. That will become the identical structure or identical configuration. This is for a C5 for the fourth time. And C5 we are passing it from the center. So if I choose my reference position where it was 1, again we got 1 there, so we can stop our operation here. How many operations have we done? We have to count. C5 for the first time, second, third, fourth and fifth. Altogether we have performed it for 5 times. So C5, when I am performing for 5 times, I am getting an identical structure. In the previous examples what we have seen is for PtCl4 2 minus tetrachloroplatinate, when I performed C4 for 4 times, we got an identical structure. Or we also had C2s. C2s which were performed for 2 times, we got an identical structure. Go to ammonia or BCl3. In BCl3 we had C3 performed 3 times, we got an identical structure. We also had C2s performed 2 times, we got identical structure. Ammonia was only having C3 and we have performed 3 rotations, we got a identical structure. So from all these what we conclude is, suppose if at all I am performing C2-2, that is giving an identical structure, therefore we are saying that C2-2 is equivalent to identity. In the case of BCl3 or ammonia, we have seen C3-3, when we performed we got identical structure. So we can say that C3-3 is equivalent to identity. In case of PtCl4, C4-4 is equivalent to identity. In the case of cyclopentadienyl anion, C5-5 is equivalent to identity. If it is benzene, if I choose benzene, we can have a C6-6 which is the higher fold rotational axis along with C2s. There it will be C6-6 which is equivalent to identical structure. So the final conclusion is Cn, when n is the fold, the same number of times you have to do the operations that will be equivalent to identical structure. This is our conclusion with respect to rotational axis. CNN is equivalent to identity. Suppose if I have a C10 rotational axis in some molecule, then I have to do 10 rotational operations to get a identical structure. All other in between operations will become equivalent, or they will produce equivalent configurations. Suppose if I am having C6 in benzene, then C66 would give you an identical structure, whereas C6 1, 2, 3, 4 or even 5, they will end up with equivalent configurations. That is our conclusion from this. Now this is not an overall picture of cyclopentadienyl anion. We are only showing a C5 in it, but along with C5 we also have some other rotational axis in it. So what are these rotational axes? Cyclopentadienyl anion, it is abbreviated as CP, cyclopentadienyl. We have seen a C5 rotational axis that is pointing towards you and perpendicular to the plane of the molecule. Along with this, there are also C2s, and where are these C2s means, you can just watch, this is like equidistant carbons. Whatever carbons that are present within the skeleton, they are at equidistant, and every carbon is identical to another carbon. So from the stereographs what we can conclude is, we have identical atoms at equidistant, the angle is also 72 degree. So since it is a 72 degree angle separation, all atoms are identical, there is a possibility for a C5 rotational axis. We have seen that C5 rotational axis. Then suppose if I am passing a rotational axis from a hydrogen carbon coming out of a bond between the two carbons, and I try to rotate by 180 degree. Suppose if I am trying to pass a rotational axis from a hydrogen which is present here as a skeleton, we are not showing it, hydrogen carbon, and as it comes through, it is coming between the bond present between the two carbons. Then along this rotational axis, if at all we rotate by a 180 degree angle, that would definitely produce an equivalent configuration. Rotate for the second time, we will get a identical configuration. So there is a C2 in this CP anion, but how many C2s are present in this? So for our considerations, what I will say is, you can just imagine this to be like a corner and this to be like a edge. This is like a polygon. Usually for polyhedra we say that there is a corner or a vertex, then there is a edge or a face. But for our considerations, what I am saying is, anyway you need not think anything to be as a face in this, it is only a polyhedra, not it is only like a polygon, not a polyhedra. So what you think is, consider this to be as a corner for our convenience, and consider this to be as a edge. Each C2 will pass from one of the corners and center of its opposite edge. That is how you try to remember for the convenience. Okay? But usually for polygons you need not say the face is present or the edges or the corners or vertices, etc. This is for our convenience. There are C2s, and these C2s are present. Where are they present? Each of them is passing through one of the corners and coming out from the center of the opposite edge. So this become one C2. Just in a similar way, when I go to the next corner, opposite is an edge, then from the center of this edge Going through the corner, we can pass a second C2. In a similar way, first corner is completed, second corner is completed. Let us come to the third corner and the center of the opposite edge. So this will become third C2. Coming to the next corner, opposite edge. So from here, if I pass a C2 and then I rotate the molecule, we'll get an equivalent configuration. And from here is the fifth C2. So what we find in the cyclopentadienyl anion is a presence of a C5 which is perpendicular to the plane of the molecule. Also there are 5 C2s which are perpendicular to this C5. This is one more introduction. Whatever secondary axes that are present in this molecule, they are perpendicular to the principal axis. The same thing you could have also seen, or you could have also noticed in ethylene. You have also noticed it in PTCl3. The same thing was also noticed in BCl3. In BCl3, I am just showing you the model for easy understanding. If this is a BCl3 molecular model, if this is a C3 that is passing from boron, the remaining 3 C2s, the remaining 3 rotational axes are perpendicular to this. So the subsidiary or the secondary axes are perpendicular to the principal axis in case of BCl3. Such a thing we have also seen in the case of ethylene. If this is considered to be the principal axis, because it is passing from more number of atoms, then the secondary axes are perpendicular to the principal axis. Take the case of PTCl4. This is a C4 rotational axis. Then we had C2s 1, 2, one type, 1, 2, another type. So we have 1, 2, 3, 4, altogether 4 C2s. All these are considered to be secondary or subsidiary, and all the 4 C2s are perpendicular to the principal axis. So likewise, even in the cyclopentadienyl anion, what we find is 5 C2s are present, and all these 5 C2s are subsidiary. They are perpendicular to the C5, which is the principal axis. This is in the case of cyclopentadienyl anion. I will try to choose one more example to show C6. This is for C5. We will just take C6, and benzene will be taken as an example. When we work out more number of examples, then we take up some inorganic molecules also, such as IF7, SF4. Plenty of such molecules will be chosen, and we have to work out what is the symmetry present in it, SiCl4, or you may choose many such molecules. This was for C5. Let us come for C6 rotational axis. And also remember, from now on I will not be doing each and every operation. For C2, for C3 and for C4 in detail I have given you all the equivalent and the final identical structure. But coming from C5 I have shown it for cyclopentadienyl, and whatever C2s that are present in that cyclopentadienyl anion, each and every structure I need not represent. You can just do it on a piece of paper. When it comes to C6, one of the best examples that is taken is benzene, which is carcinogenic. It is banned in most of the countries. In our country it is still used in some labs, which should not be used at a very higher proportion, because as I said, it is a carcinogenic agent. It can cause cancer. So when it comes to benzene, it is only a skeleton where hydrogens are not represented, and these are considered to be the carbons which are equidistant. And the angle, suppose if I rotate, when I rotate by a 60-degree angle, one carbon will exchange with another carbon. So when I am rotating by a 60-degree angle where the carbons are being exchanged with one another, 360° upon 60° would give you a C6 rotational axis. So it is a 6-fold rotational axis present in benzene, and that rotational axis is perpendicular to the plane of the benzene. It is just pointing towards you. I repeat this point several times. Symmetry mainly depends on our imagination. Suppose if I say some molecule, immediately I have to create that particular molecule geometry. Then you have to imagine that you are passing some symmetry element through that molecule, how the operations are being carried out, then what is the final structure, how many operations you have carried out, whether you are getting symmetrical structure or not. All these things have to be done, which takes some time. In the beginning you have to put a lot of examples on paper, but as you practice day by day, you can just imagine the molecule and you can tell what is the symmetry element present in it. So here we have a C6, and that C6 is passing perpendicular to the plane of the benzene. This, as I told you, for convenience consider it as a corner. Altogether we have 1, 2, 3, 4, 5 and 6 corners for a benzene. For these corners, for convenience, what we will do is we will take one pair of opposite corners. For this corner, this is opposite, these are adjacent, this one is opposite. So from one pair of opposite corners, let us try to pass one C2. I have chosen one pair of opposite corners, I am trying to pass a C2. This C2, whenever I say pass it, this is passing from the center, but if I draw lines in the center, it will be very fuzzy. Every time if I put lines in the center, you may not see the structure properly, so we avoid drawing the lines in between. We simply put here and again we start it from here. It simply means it is passing through the molecule, right. So one pair of corners is completed. Let us come to the second pair of corners. For this corner, this is the opposite. Let me pass a C2. If this is one C2, this is another C2. From here is a third C2. We have seen a C6 that is present in the benzene. Along with this C6, now we are able to see C2s, 3 in number. Each C2 is passing from a pair of opposite corners. Do we find any other rotational axis apart from this C6 and 3 C2s? If you very carefully look at the molecule, you just try to figure it out. Do you see any other rotational axis apart from C6 as well as the other 3 C2s present passing from the opposite corners? These are considered to be as edges. We have 6 edges in this benzene, and let me choose one pair of opposite edge. For this, this is opposite. So from the center of these opposite edges, we can see another C2. From the center of these opposite edges, one more C2 can be seen. If that pair is completed, let us come for the second pair. There is a C2. So I am passing it from here, rotate the molecule by 180 degree, and third one can be visualized here, C2. Apart from this, do we find any other rotational axis? If we very carefully look at the molecule, then the answer is no, we do not find any. We have a C6, along with this C6, we have 3 C2s that are passing through pair of opposite corners. We have C2s that are passing through a pair of opposite edges, and there are 2 different types of C2s. So one C2, the another one we just try to put it as a C2 prime, because C2 is passing from more number of atoms. Each C2 is passing from 4 atoms, hydrogen, carbon, carbon, hydrogen. So it is passing from 4 atoms, whereas the C2 prime is passing only between the atoms. It is not passing only from the bonds. It is passing between the atoms, passing only from the bonds. So I have labeled it as a C2 prime. We have a C2, we also have a C2 prime, 3 C2s, 3 C2 primes and a C6. So altogether there are 7 rotational axes. The higher fold one is a C6. This is considered to be the principal axis. All these are considered to be subsidiary or secondary. So we have a 1 C6, 3 C2s and 3 C2 prime. C6 is considered as the principal axis and these are considered as secondary. This is for C6. So as we go for a higher fold, C7, C8, the number of molecules drop, as I said. If at all you want a C7, the example given is tropylium cation. This you can do it as an assignment. You can show C7 rotational axis in tropylium cation. Along with that C7, you also find there are 7 C2s present in it. C6, benzene C6, 6 is a even number. C7, where 7 is an odd number, so definitely for a corner, opposite will be an edge. Even in C5, previously in the previous example, what we have seen is for C5 cyclopentadienyl anion, for a corner opposite was a edge. It is odd number for odd number polygons. C6 even number, so for a edge opposite will be edge, for a corner opposite will be corner. For tropylium, for a corner opposite will be edge because it is odd number. And for C8, I am giving you cot dianion, where cot represent cyclooctatetraenyl dianion is the example for C8. There is a C8 rotational axis in it. Along with that, there are 8 subsidiary axes which are perpendicular to C8. So those 8 C2s, there is a C8 plus 8 C2s. These 8 C2s can be seen as 4 C2s and 4 C2 prime in this case because it is even number. So half of them will be passing through a pair of corners, the other half will be passing through a pair of edges. Whereas in this case there is a C7 and 7 C2s and every C2 is similar because every C2 will pass from a pair of a corner and its opposite edge. You just try to put the figure of tropylium cation and also cot dianion and you try to put a C7, C8 and also 7 C2s and 8 C2s in them. Then you can compare whether you are getting 4 C2s and 4 C2 primes or not. In this case you have to get a C7 plus 7 C2s. There is no differentiation in it. All C2s will be the same in C7 or odd number ones. With these examples, we can conclude the rotational axis of symmetry. What exactly is rotational axis of symmetry? It is an element. We said all symmetry elements are imaginary. By definition, suppose if anyone asks you what is the definition of rotational axis of symmetry, then in a very easy way we can define. It is that symmetry element. It is an imaginary. It is always remember that it is an imaginary element. Okay, it is an imaginary symmetry element which pass through the center of molecule. When I say center, it is understood that it is the center of gravity. So it is that imaginary symmetry element that pass through the center of the molecule, around which when rotation operation is carried out will bring the molecule into a configuration that is indistinguishable from the original one. That can be the definition of rotational axis of symmetry, which is represented by Cn, which is a Schoenflies notation. When it comes to the workout, I will just give an example. You may try to work it out what rotational axes are present in it. The example is H2O2. So you can just pause the video. You can work out what rotational axis is present in hydrogen peroxide. Along with hydrogen peroxide, the most important example, and which is very frequently asked in most of the competitive examinations, is allene. Once allene was asked for its point group, once COEN thrice was asked for its point group, and these were asked for 4 marks in CSIR. If you are able to get the point group of it, you can just score 4 marks. Also, I would like to stress one more important point. There are some students who try to skip symmetry and group theory because they find it little bit difficult, since there are n number of molecules, and each and every molecule you just cannot get all the symmetry elements, or you cannot define the point group for any given molecule. But there are some logics. As we go on doing some examples, you practice more and more examples. As we practice more and more examples, whatever molecule that is given to you, if the geometry is known to you, because whatever molecules that you have in your database, in your knowledge, all these molecules you have been seeing from your school, +2 and undergraduation level. So even at PG level you will be going through many molecules. All those molecules will be in your database, that geometry will be known, and most of the examples that they ask in the examinations will also be related to those molecules. So just get the geometry, and once there is a geometry in your brains, then you try to pass a symmetry element, give the point group, and there will be your answer. Only thing is you have to do more number of examples. So coming to the hydrogen peroxide and allene, these are considered to be the most important examples. Whenever hydrogen peroxide is given, some students they start doing the symmetry elements and immediately they start giving the answers. But the first question that you must be putting yourself whenever hydrogen peroxide is given is, what is the conformation of that hydrogen peroxide? That is to be asked at first. Since in hydrogen peroxide we have 2 oxygens where they are getting separated by a single bond, there could be a single bond rotation, and once there is a single bond rotation, you will get some different conformations. So what are these different conformations? I am trying to show you with respect to a molecular model. If this is the hydrogen peroxide, these 2 red ones are considered to be the oxygen atoms, and these 2 are considered to be the hydrogens. So in this conformation, what we find is, this is considered to be a cis 1. This is considered to be a cis 1. There is a single bond rotation, and as it rotates, as you can see, as it is rotating, now this one is called as a open book shaped hydrogen peroxide. This one is a open book shaped hydrogen peroxide, and as the rotation continue, what conformation that we get, we can call this as a trans. So in hydrogen peroxide is asked, we have 3 different conformations. One is called as a cis 1. The second one you can call it as a skew or an open book shaped hydrogen peroxide, and the third one is considered to be the trans. So we have to draw all the 3 structures of the hydrogen peroxide, and then we have to see which rotational axes are present in it. Hydrogen peroxide is not that easy as we think. First let us start with a cis. Then let us put a trans. Here is another hydrogen, it could be away or towards you. A dotted line represents it is not in the plane, it could be either towards you or it could be away from you. This is skew form or open book shaped. This is the cis and a trans form. Now let us start with the cis one. I am holding the 2 hydrogens below. It is just similar to water molecule. If you can just look at this, it is just looking like a water molecule where there was one oxygen in the center and two hydrogens attached. In this case, we are just like dragging it. That one oxygen has now become two. So in water molecule, that rotational axis was passing through the center of oxygen. Now it is passing in between the oxygens. If you can just pass it from here, then try to rotate by a 180 degree. It is giving you an equivalent configuration. Then rotate by another 180, that will produce you identical configuration. Right? In the case of cis H2O2, we can see a 180 degree rotation. Can I pass a C2 from here? If I rotate by 180, the two hydrogens which were to the bottom side, now they are coming above, so it is not a valid rotation. This particular C2 is absent. If at all you are trying to imagine the coordinates, when I am holding the molecule in this particular orientation, this becomes Z, this becomes X, this becomes Y. Along Z, if I pass a C2 rotational axis, C2 is present. Along X, if I try to pass, that C2 is absent because the two hydrogens are going up. Along Y, if I am trying to pass, the two hydrogens which were down, now they are facing up. So this is absent, this is also absent, but this is present. So there is only one rotational axis C2 that is passing between the two oxygens, around which if rotation operation is carried out, it will bring an equivalent configuration, that is for cis. Now let us look for the trans. This is a trans conformer. Within this trans conformer, suppose if I am holding the molecule in the same manner which I have held it for the cis one, if I try to pass the rotational axis from Z, now this hydrogen atom, if it is taken as the reference, this is towards your top right. That top right, as I rotate, you can see it is coming to your top left. Top right and top left, they are not equivalent configurations. So a rotational axis which was passing through Z in the cis conformer, here you can see that is absent now. Let us try to pass it from Y coordinate. Again, you will just take the reference of a top hydrogen atom which is top right towards you. As I pass a 180 degree angle, that is coming to the bottom right. So this particular rotation axis is also absent. Now let us come to the X. I am trying to pass a rotational axis from X coordinate. This is a top right one. If at all there is an atom which is exchanging this top right, we have such a C2. You can see again at top right there is a hydrogen atom. It means there is a C2 rotational axis, but this C2 rotational axis is passing through X coordinate. So in this case, since it is passing through the X coordinate which is facing towards you or which is pointing towards you, you have to just put a dot around which do the rotation operation, and that will produce an equivalent configuration. Coming to the last one, it is an open book shaped conformer, or you can call it as a skew. Some represent it as a Gaussian. Which rotational axis is present in it if I am trying to hold it this way? Now let me pass from here. Let me pass it from, let's say, Y. Both the hydrogens are up. As I rotate by 180, they are coming down, so it is not present here. Let me pass it from X. Both hydrogens are up, they are coming down. Now as I am passing it from the Z, there is a top hydrogen towards your right hand side. Top right is a hydrogen. If it can be replaced by another hydrogen, you can see now again it is replaced by a hydrogen. So there is a C2 that is present between the OH and OH unit. Now I am showing it this way. In this manner you can understand it well. Now towards your top left there is a hydrogen. Again if I rotate, there should be a hydrogen at your top left. There is a hydrogen at your top left. This is the reference point. If you take this as a reference point which is away from you, This is a top right with respect to you, top right but away. Again at top right away you should get a hydrogen. Top right away you are getting a hydrogen. So there is a C2 rotational axis, but there is only one C2 rotational axis. No other C2s are present. Whether you take cis, whether you take trans, or whether you take a skew or a open book shaped one, we find only one C2 to be present. There is no other C2 which is present in it. Getting back to allene, allene is a non-linear, it is also a non-planar molecule. If we look the molecule very carefully, what we find is it is similar to ethylene, CH2 unit, CH2 unit, but there are a lot of differences. The difference is there is a central carbon which is connecting the two CH2 units. In the case of ethylene, it was only two CH2 units which were connected with the bonds. In this case, the two CH2 units are connected with a carbon. That is the first difference. Second difference, in the case of ethylene, what we found is, if this is the ethylene, I am just trying to compare ethylene with allene. Now let us compare ethylene to allene. Ethylene, we can see a CH2 unit separated by a bond. Here we have a CH2 and a CH2 unit separated by a carbon. Second thing, the two CH2 units, they are in plane. You can just watch, they are in plane, and if at all you are looking in this direction, they are eclipsed. This CH2 unit is eclipsed over this CH2 unit. If I exactly hold it this way, they are eclipsed, therefore you are not able to see a CH2 unit which is away from this. The rare CH2 unit cannot be seen. Hence we can say it is a eclipsed conformation or an eclipsed molecule, right? When it comes to the allene, one CH2 unit and the other CH2 units, they are not eclipsed. Instead they are staggered. You can just call them as a staggered one. They are not eclipsed, you can just call them as staggered one. This is not a conformer, you just remember, it is not a conformer where I am trying to rotate and then I am trying to say that eclipsed is converting into staggered. But just for our understanding purpose, what we say is this CH2 unit is eclipsed over this CH2 unit, but this CH2 unit is not eclipsed, so for that reason we are simply calling it as a staggered kind of a conformation or staggered kind of a molecule. That is the difference between this ethylene and allene. Ethylene is a planar molecule, non-linear one. Allene is a non-linear, also it is a non-planar molecule, because one of the CH2 units, suppose if I am taking this particular plane, a YZ plane, within this YZ plane these two hydrogens do not fall. One hydrogen is facing towards you, one is away from you. So this exactly has been drawn here. One hydrogen above, one hydrogen below the plane, one hydrogen away and one hydrogen towards you out of the plane. So these two hydrogens are in plane, these two hydrogens are out of the plane. When we draw allene in this manner, it becomes little bit difficult to show the rotational axis. Instead, let me put one more diagram. If this same allene as I am holding it, now instead of looking from this end, let me look from this end. So from your point of view, you are not watching the molecule in this way, you are trying to watch the molecule in this way. Now as you are watching it in this way, it is pointed from this carbon with respect to this. One hydrogen is above, one hydrogen is below, and these two hydrogens on the rare carbon, one is towards your right hand side, another is towards your left hand side. So if at all you can represent in this Newman projection, let me put it. It is that same allene, but in a different view, and this view will be more important for our symmetry considerations, because it becomes very difficult for any student to show the rotational axis in this diagram, but in this case it becomes very easy. How it becomes very easy, let us see. Now when I am holding the allene in this manner, just as in ethylene where we passed a rotational axis from two carbons, let me show in this way. In ethylene there was a C2 that is passing from the two carbons, around which if rotation operation is carried out, it is bringing the molecule into equivalent configuration. So likewise, let us also take allene, pass a rotational axis that is passing from the three carbons right now, and let me try to rotate by 180 degree. It is giving you equivalent configuration. This was the original one. If I am taking this reference on top, which is towards you, as I rotate, that is going to the bottom, but it is looking similar to the original one, so we are calling it as a equivalent configuration. There is a C2 which is present in allene and it is passing from the three carbons. I am also showing in another way. This is that rotational axis. These two hydrogens are in plane of the board, or they are in this YZ plane. As I rotate by 180, it is giving you equivalent configuration. So as I am showing this, this is that C2. It is a C2 that is pointing towards you, and around which we are carrying out a rotation operation. In this case, it is this. It is a C2. Apart from this C2, if you can figure out any other rotational axis, you may just take a couple of minutes of time, and then you just try to check whether you find any other rotational axis in it. If at all you are finding any other rotational axis, how are you able to represent it? Try to represent. And if you are not able to represent it, let me tell you, suppose if I am holding it this way, this was a C2, I am holding it this way, now this is that C2. Apart from this, now just let me put a rotational axis here on the central carbon atom, just perpendicular to this C2. Let me put it here. As I put it here, now you can see these two hydrogens towards you. These two hydrogens are towards you. They are above and below the plane, xy plane. If I choose, they are above and below the xy plane. If I rotate by 180, you are getting two hydrogens which are in the plane xy. Above and below the xy plane cannot exchange with two hydrogens in the plane, so this is not a valid rotation. Then I conclude that there is no C2 which is passing from the central carbon atom. Also, let me check by passing it from here. Then I rotate by 180. This is a CH2 which is just like what can I say, if this is an xy plane, one hydrogen is above and one hydrogen is below the xy plane. I am trying to rotate by 180. Now I am getting two hydrogens within the xy plane. So by holding the molecule in this way, then I come to a conclusion that there is only one C2 which is passing through the 3 carbon atoms. There is no other C2. Even if I am trying to pass it from the central carbon atom, I am not getting a valid rotation, therefore the other C2s are absent. There is only one C2 in allene. If I conclude the same, then we are wrong. We are wrong. Why are we wrong? Look at the same allene very carefully. Holding the molecule is also very important. This was told in the prerequisites. In the prerequisites that are required for passing the symmetry elements, 3 prerequisites have been mentioned. One was the knowing of geometry. There should be a decent knowledge of geometry, without which you cannot draw any structure and you cannot pass any symmetry element. Also, center of gravity should be identified in a given molecule. I just cannot pass a rotational axis from the rear carbon or the front carbon. In allene, it is identified that the center of gravity will be in the second carbon or the central carbon atom. So here center of gravity is present. Now how should I pass the rotational axis? Suppose if I am trying to pass it through here, it is absent. But what we find in the literature is allene has 3 C2s. There are 3 rotational axes, or better you can call it as 3 rotational axes. Where are the other 2? To visualize them, now previously when I held the molecule in this way, we were trying to pass a rotational axis from the central carbon, where the rotational axis is in parallel to this hydrogen or exactly perpendicular to this hydrogen. This is how we have performed it. The other one we have performed in this way. Now instead of performing it here or here, let me try to perform it here. From here is one C2 and from here is another C2. So if I am performing this C2 and as I rotate, you can just check these 2 hydrogens that are towards you are above and below the xy plane. So if I am trying to pass a rotational axis from here, as I rotate, again you are getting 2 hydrogens above and below the xy plane. So we say that there is one C2 that is passing only from the central carbon atom. There is also another one from here, just like the previous rotation that we have performed. So this is one, this is a second one, and this is a third one. Altogether there are 3 C2s. This could be little bit difficult for you. So how am I rotating this way? So this rotation become difficult for you to imagine. Then instead of holding the molecule exactly in this orientation, let me try to hold it in this way. I am just showing to the cam. If at all you can look at the molecule, what you are able to see is like a X. You are just able to visualize an X. Instead of holding the molecule in this way, I am just tilting the molecule to some angle, so that instead of looking like a plus symbol, now you are looking like a multiplication symbol. In this multiplication symbol, these two hydrogens, you just imagine that they are in line. You just imagine it, though they are in the front carbon and the rear carbon. Now, as I hold it in this way, you take reference of one hydrogen. Which hydrogen will you take as a reference? It is up to you. But for the explanation purpose, I am trying to take this particular hydrogen, which is towards your top right. With respect to you, it is top right. I am holding the central atom now. Now exactly from here I am passing it. In the previous case, when I am holding in this way, it was the C2. Now I am trying to hold it in this manner. Top right is a hydrogen which is towards you. Then you rotate. Top right is a hydrogen. So there is a C2 rotational axis. Did you get that? This is a C2. You may choose any reference as you like. So this was one C2. Now I am trying to pass another C2 from here. You can take the reference of this again. If at all I get a hydrogen here, then a C2 is present. So just let me rotate. You are getting a hydrogen here. Still it will look like a X or a multiplication symbol exactly when you look it from here. Right. So how many C2s are present means the answer is altogether there are 3 C2s. One C2 is passing through the 3 carbons, the other 2 C2s, they are perpendicular to the main C2, but they are not exactly in this way, they are in this way. Or you try to hold it, the molecule, then you pass. This is one C2 and this is a second C2. How do you show it in the representation? In this case, since this is how I am holding it, so one was here and the second one was coming from here. So it is like 1 and a 2. Maybe this looked like a little bit crude representation if at all we choose to represent the allene in this manner. But in this projection, we can very nicely show it. This is how the molecule is. Now this is one C2, this is another C2. So wherever you get such kind of molecules, this is one of the best logics that I can explain. The best logics is whenever you have molecules where the 2 units are staggered to one another, draw such a molecule in this Newman projection, and once you draw it in this projection, what you get is a space between these atoms. This is the front carbon and this is the rear carbon. On the front carbon, whatever you have, you just think them to be corners. Wherever you have atoms, you just make them to be corners. Between these corners is some space. This space I call it as a groove. This is my way of explaining to the students. So maybe you will not find it in any literature, so don't bother about it. This is for our understanding. What I am telling is the opposite hydrogen atoms, you just consider them to be corners. These are also corners. Now between these there is some space. These spaces I am calling it as grooves. From the opposite groove or this from opposite space, you try to pass a C2. And that is completed. So let it be staggered let it be staggered ethane, not ethylene. Let it be staggered ethane, or you choose any such molecule. It could be staggered ferrocene, it could be staggered chromosine, where there are 2 units that are staggered to one another. In such cases, if at all you put it in this kind of a projection, then you will definitely get some spaces in between. Those spaces, let us call it as groove. Then from the opposite grooves, C2s will pass. From the opposite grooves, C2s will pass. This is applicable to all such molecules. In this case, we are taking an allene, we are able to show a C2. If at all we take eclipsed ethane or staggered ethane, in staggered ethane, such a conformation will again appear. Not eclipsed, but staggered if at all we consider, again we will get some grooves. There we can show C2. So how many C2s are there altogether? One C2 that is passing from 3 atoms, that is considered to be a principal axis. These 2 are considered to be subsidiary. In allene altogether there are 3 C2s. One C2 that is passing from the 3 carbon atoms, the other 2 C2s they are passing from the central carbon atom and perpendicular to the main C2. Why am I stressing a lot on allene is it is very important for you to understand it. So I am showing all the possible orientations of allene, and this C2 is very easy to visualize, either in this orientation or in this orientation. It is very easy to visualize. But when it comes to this C2, here it is absent, here it is absent, but it is passing in this way, just like diagonally when I am holding it in this manner. Instead, if at all you can hold it this way or this way, exactly from the point towards you, it is like a, it will just look like an X. Then in such a case you can pass a C2 from here, another C2 from here. As you rotate, it is giving you an equivalent configuration. Or if I hold it here, that is giving you an equivalent configuration. And for all such molecules where there are identical units, I am not saying that if one is CH2, another is CBr2 and so. These two units should be identical, and if such identical units are staggered to one another, put it in a Newman projection, then from the opposite groups C2s will pass. Okay, this is about allene. Apart from allene, CO trisethylene cobalt, it is a little bit important example, and we will arrive to all such examples at a later stage once we discuss about the point groups. But in the beginning cases, what we have discussed till now is restricted to the rotational axis of symmetry, where we have taken some different examples, and your view on these molecules must be in such a way that you have to imagine the molecule in different orientations. Ethylene, generally it is put in this way. Try to put ethylene in this manner, try to put it in this way, try to put it in this way, and then pass the symmetry elements. And as you do this, upon practice, molecular symmetry become very, very easy. So there will be a point where we can start playing with these molecules. Start playing in the sense, once I give you some molecule, you can just start playing, okay, whether plane is present in it or not, whether inversion is present in it or not, if at all there is any rotational axis, from which atom is it passing. All these things can be done very, very easily. In our next class, we will discuss the next symmetry element, which is plane of symmetry.